Hello, everybody. This is Sunday. It's November 27th, and we are going into week 13, module 13 of our online astronomy course. Hope you all had a good Thanksgiving, and maybe during Thanksgiving, during that time period that you didn't have anything scheduled for this course, I hope you had a chance to take a look at the Artemis mission. Artemis is the successor to Apollo. 50 years after the Apollo missions, the Artemis mission is sending a rocket around the moon. And it's really sort of cool because tomorrow, on Monday, Artemis is going to set a distance record from Earth. Tomorrow it's going to be uh, as far as any human-carrying spacecraft has ever gone from Earth. It's the previous record was held by Apollo 13, and this is going to be about 30,000 miles farther than Apollo 13 went and far beyond the moon. Now, this mission is not manned, but the next one, if this mission is successful, will be manned. It won't land on the moon, but it will orbit the moon several times and then return to Earth. And then the one after that will be a landing mission and will land astronauts on the moon. So pretty exciting to think about. And here's a picture. This is from a camera mounted on the solar wing, the solar panel of the spacecraft. And here you can see the camera sees the Artemis capsule that the astronauts will be in and looking back at our planet Earth. And now it's going to be orbiting the moon for 6 days in this wide orbit. And then it will come back to Earth and it will arrive back on Earth, I think on, gee, I'm trying to remember when it was. It's a couple weeks into December. So pretty cool stuff. Now, I also want to give you another reminder, and that is that the course evaluations, the evaluations for this course that students do are now available. And you've received an email about that. And those are due on Thursday, and that is the 1st of December. So that's the last date you can do those. I'd just like to encourage you to do those. You can give a numerical rating as well as make some comments. And the comments are especially valuable to me. You know, if there's something you liked, let me know. If there's something you didn't like, please let me know. Because I have changed the course, altered the course in the past. I do listen to the student comments. I read them all. And of course, those get sent on to the department chair and the dean and, you know, whoever I guess wants to look at them. I don't know. But yeah, please do that. I know some of you have. About 30% of the people in the class have done that. But for the rest of you, if you haven't, and you get a chance, please do that before this coming Thursday, December 1st. Okay. Now we're going to talk about galaxies. And last week, you learned about our Milky Way galaxy, and that is the galaxy that you see here in the sky, the great arch of our Milky Way galaxy spanning. This is the between the Temple of the Sun and the Moon here in one of our Utah national parks. And every star you see in the sky here belongs to our Milky Way galaxy. But there's one thing that doesn't, and that is right here. This little smudge is the Andromeda galaxy. It's sometimes called M31 for short. It's entry number 31 in a catalog of objects compiled hundreds of years ago by Charles Messier. So it's Messier object 31, M31, or just the Andromeda galaxy right here. And that is, excuse me, please, That is the nearest galaxy to our own Milky Way galaxy. It is the nearest large spiral galaxy, I should say, that is much like our own Milky Way galaxy. And it is about 2.5 million light years away. That's 776 kiloparsecs. Now, our own galaxy is about 30 kiloparsecs across. And so this is something like 28 times the distance across our galaxies, how far it is to the Andromeda galaxy. It's very far away, and it's the farthest thing you can see with your naked eye. Now, what's cool is that you really don't have to go out on a dark night and a really dark place to see it, because I went out one night into my driveway and I looked up, and there it was. There was Andromeda. So I'm going to show you that right here. This is right over my shoulder right here. That little smudge is Andromeda. Boy, my throat is getting terrible. Excuse me. That is the Andromeda galaxy. I was just looking pretty much straight up from my house. In fact, if I just move to the side here, you can see sort of the top of my chimney poking here just over my shoulder. There's the top of my chimney right about there. Just look straight up, and there was Andromeda. And later, when I show you Stellarium, I'm going to show you how to find Andromeda in the sky. But if you take a close look at Andromeda through a telescope, of course, then you see the full galaxy. And here is the Andromeda galaxy. I'll move to the side so you can see it a little bit better. It is a flat galaxy. You can tell that it's flat. It's in a disk like this. Here's the nucleus of the galaxy right there. And it's a little bit larger, in fact, than our own Milky Way galaxy. So this is the nearest large spiral galaxy to our own Milky Way. And we didn't even know there were other galaxies until about 100 years ago. And that's when Edwin Hubble discovered a Cepheid variable star in Andromeda. And, at first he thought it was a nova. And then he realized he was wrong. It was a Cepheid, and he got all excited. And that is the first time we realized that these shapes of gas that you can see through telescopes were not smaller objects lying inside our Milky Way. They were huge galaxies in their own right, existing far beyond our Milky Way galaxy. So, galaxies come in several types. There are spiral galaxies, like our own Milky Way has spiral arms. So does Andromeda. And there are two types of spiral galaxies. There are just regular spirals, and there are what's called barred spiral galaxies. And those galaxies, right at the center, they have a little bar coming out from the center, and then the spiral arms move out from there. There are elliptical galaxies, which are really big football shapes of galaxies. And then there are irregular galaxies that really don't have any well-defined shape. Now, how many galaxies are there in the universe? Well, you might remember that there are several 100 billion stars in our own Milky Way, and there are as many galaxies in the universe as there are stars in our Milky Way. So several 100 billion galaxies in our universe. Just amazing. Now, with the wide separation, here I've talked about how Andromeda is very far away compared to the size of our Milky Way galaxy. We tend to think of them as just being like island universes. In fact, that was a phrase that was used for the galaxies, island universes, early on. But today we know that's not true, that galaxies interact with each other. They can gravitationally attract each other. And when these galaxies collide, it's not stars actually colliding, because the stars are so far apart that the stars in the galaxies just pass right through one another. But the gas and dust in the galaxies does collide, and that can create a huge burst of star formation. And in fact, galaxies can even merge together. And you can have ellipticals merge with a spiral to form a larger spiral, and all sorts of things can happen. And in fact, our Milky Way galaxy is going to merge with Andromeda in about 4.5 billion years. And that's going to be about the time when our sun is on its way to becoming a red giant and swallowing Mercury, Venus, and Earth. And the Milky Way and Andromeda will merge, and that merger will be accomplished after about 5 billion years. So where there were two galaxies, there will only be one. And we see that going on a lot in the universe. So it's really pretty amazing. It's an amazing thing. And this is called galactic cannibalism, when one galaxy devours another, and they merge. And there's evidence that our own Milky Way galaxy has devoured a nearby galaxy in the past. So we have a universe filled with galaxies. And in 1929, Edwin Hubble discovered, he looked at the galaxies. Remember, if you look at the spectral lines of the stars in a galaxy, those spectral lines can be shifted, Doppler shifted. They suffer a redshift. They're moved to longer wavelengths if they are moving away from us. And Hubble looked at a number of galaxies, and he could also tell their distance, just by finding Cepheid variable stars. And Hubble discovered that all of the galaxies that he could see were moving away from us. And in fact, all of the galaxies are moving away from all of the other galaxies. So the distance between galaxies is increasing with time. Now, you may wonder, but wait, I just said that, Andromeda is going to collide with the Milky Way. And now you're telling me that all the galaxies are moving away. Well, galaxies come in groups called clusters. And the Milky Way and Andromeda belong to the same cluster of galaxies. It's called the local group. So we are members of the local group of galaxies. And the galaxies within a group or a cluster are all gravitationally bound together, so they can come together. But once you go to galaxies that are outside of our own cluster of galaxies, all those galaxies are, in fact, moving away from us. And not only that, they move away in a very particular fashion. If I compare, like, how fast is one galaxy moving away from us versus how fast another galaxy that's farther away is moving away, I find that the galaxies that are farther away from us are moving away faster. And in fact, a galaxy that's twice as far away from us is moving away twice as fast. And today, we call that the Hubble law. Galaxies twice as far away are moving away twice as fast. Galaxies 3 times as far away are moving away 3 times as fast. And in fact, if I take the distance to a galaxy in millions of parsecs, and let me say a word about this first. In our own galaxy, is 30 kiloparsecs across. Distance to Andromeda is 766 kiloparsecs. So we need another distance unit, a larger distance unit, to talk about the distance to galaxies. And so we're going to talk about millions of parsecs, megaparsecs. And so megaparsec is 1,000,000 parsec. That is 3,260,000 light years. So when Hubble was describing how all the galaxies are moving away from each other, he measured distance in megaparsecs. And it turned out that for every megaparsec of distance that a galaxy was away from us, it was moving away 70 kilometers per second faster. So if a galaxy is 1 megaparsec away from us, it's moving away from us at 70 kilometers per second. If a galaxy is twice as far, 2 times 2 megaparsec away, it's moving at twice 70 kilometers per second, or 140 kilometers per second. If a galaxy is 3 megaparsecs away, it's moving at 3 times 70, 210 kilometers per second away from us. And that is the Hubble law. And that allows us to find distances to very distant galaxies. Maybe we can't, find Cepheids on them, but if we can measure how fast they are moving away, we can find out how far away they are. And for instance, let's say, and I'll just choose this, let's say that a galaxy is moving away at about, 28,700 kilometers per second. Just to pick a number, not off the top of my head. I have it, written down here in my notes. But if a galaxy is moving away that fast, all you have to do is divide by 70 to get its distance, and you find out that galaxy is 410 megaparsecs away. Pretty cool, pretty cool. Now let's think about what that means here. We're looking at things that are hundreds of millions of light years away from us. And that means we're seeing the galaxies not as they appear now, but as they appeared hundreds of millions of years ago. We're seeing the Andromeda galaxy as it appeared 2.5 million years ago. And so telescopes are time machines. We don't have to, if you're studying early life and you would go out to Wyoming or someplace and dig into the ground and find fossils of dinosaurs or ancient plant life, there you have to rely on the fossils to tell you what that life was like. We want to know what the early universe was like. We look at it through telescopes because we're looking back at time, at light that has been traveling toward us over hundreds of millions or even billions of years. And so we can see the early universe. And the early universe was not like it is today. There were galaxies there that we don't find close to us in today's universe. And those galaxies emit huge amounts of energy. They're giving off huge amounts of energy, and they are called active galaxies. And at their center, or the nucleus of those galaxies, are called active galactic nuclei. And we just call them AGN for active galactic nuclei. And those are powered by supermassive black holes at their center. And there's matter that tries to get into those black holes and can't. Huge pressure builds up because the matter just can't flow in fast enough. And so it gets squirted out in 2 directions, in 2 opposite directions. Imagine, it's sort of like if at Thanksgiving that you had a big ball of mashed potatoes in your hand, a big ball of mashed potatoes, and you just sort of smashed it from both sides. What would happen? The mashed potatoes would have squirted out, top and bottom. That's what happens in these active galactic nuclei. And these jets of material are shooting out at speeds close to the speed of light. So just fantastic things are going on. And I've already mentioned how galaxies are arranged in clusters. We have our own cluster, our own local group of galaxies, about 40 galaxies in it or so, a little bit more than 40 galaxies. And that's not very many. It's called a poor cluster of galaxies. But there are rich clusters that have hundreds or thousands of galaxies in them. And those galaxies themselves, those clusters of galaxies, are arranged in superclusters. And those superclusters are arranged through space like a web, as though they were on the surfaces of bubbles. And in the inside of those bubbles, there are regions of space where there are no galaxies, or very few galaxies, almost none. And those are called galactic voids. So where did this structure of the universe come from? It's just amazing to think about. And we're going to find out about the origin of this structure next time in our last module. And there's more surprises yet. Around all of these galaxies, including our Milky Way, there's a halo of dark matter. And you already found out about the Milky Way's halo of dark matter last time, but all galaxies have a halo of dark matter. And it turns out that there's about 6 times more dark matter in the universe than there is the bright, pretty shining stuff like stars and gas and glowing gas and things like that. We don't know what the dark matter is. We know it's there. We can see how it's distributed by looking at its gravitational effect, but what is it? We don't know. And so what a joke on astronomers. Here we've been studying the bright, pretty, shiny stuff, the sparkly stuff, and that's only a small fraction of what's out there. Pretty cool. So that is the universe of galaxies that you're going to be learning about. And I want to, before I leave, show you a little bit about what's in the sky this week and show you how to find Andromeda. I know winter's a terrible time to try to find things because the skies are often cloudy. But the cool thing is that Andromeda is visible anytime during the year. Now, sometimes it's higher, sometimes it's lower, and it turns out this is a pretty good time to see it. So let me go on, and here I'll pull up Stellarium. There we go. So let me pull up Stellarium. There it is. And so this is showing you what the sky will look like if you were looking southwest. This is around 7 o'clock at night. And this is on Monday, the 28th. And you can see this is a first quarter moon, and it's right below Saturn. That's really cool because over here is, I'll just move the sky a little bit, Jupiter. And over the next several nights, the moon will be traveling along. And on December 1st, it will be right under Jupiter. And that's the last day to, as I said, do your evaluations if you want to. I hope you will. Now, let's see where Andromeda is. So to see where Andromeda is, I'm just going to turn around here. Here we go. There's Mars. I'm going to have to, this is looking right now a little bit northeast, east-northeast. I'm going to go up. I'm going to zoom out a little bit. Here we go. And here, looking high in the sky, is the big W in the sky, and that is Cassiopeia. This is Cassiopeia, the big W in the sky, and let me just show you the W there in the sky. There we go. It's the throne of Queen Cassiopeia. But notice how these 3 stars seem to form a pointer. These 3 stars seem to form a pointer. And if I go out, if I think of this as an arrowhead, and if I go out about 2.5 arrowheads from the tip, I get to here. And if I just go upwards a little bit, toward that top star in the arrowhead, then I find the Andromeda galaxy. There it is. Now, it will appear to be just a smudge, but it is Andromeda. And I think it's pretty cool to look at something in the sky and know that you're looking at something that the light left 2.5 million years ago. Pretty cool. So I hope you enjoy learning about the galaxies, about how galaxies are arranged in space, about their structure. And next week, Module 14, our final one, we'll be looking at where did all this come from? And I think that you'll find that very interesting. So I hope you have an enjoyable week, and I will look forward to seeing you next time. So until then, bye-bye.